just for giving me the opportunity to talk here. I also want to thank one of the previous speakers, Anuradha, for the nice videos of interviews with Rohini she showed us. Because among other things, I learned of one more person I should be grateful for. Rohini, in one of the interviews many years later, expressed her gratitude towards the department chair at Bombay University in 1985 who let her go on a 2-year leave of absence, even though she hadn't been there 2 years yet. And in these 2 years, she went to Dortmund, and that's where I met her. So I should be grateful to that chairperson as well. Rohini was the first female physicist I actually got to know. In my own year, I studied in Dortmund. There were starting about 90 or so physicists or students, out of which there are only 3 women. Things have, gender balance has improved a little bit in Germany since then, but still females, of course, are distinct minority in physics still. And Rohini was also the first professor who treated me as an equal. I had just finished my PhD when she arrived in Dortmund, and at that time, at least, there was still a wide chasm between students and professors in Germany. We didn't actually collaborate. We had only a few months overlap. She arrived, if memory serves me right, in early summer, and I left in October to start my first postdoc position. She did make me take her to an English language screening of a movie, which she somehow had found in Dortmund. Dortmund in those days was quite a provincial place, so it was not easy to find movies in the original version, but somehow she found a screening of a movie version of Kipling's The Man Who Would Be King with Sean Connery. I still remember that. She made me drive her there, and yeah, I enjoyed the movie too. Anyway, we started to collaborate only when I was in Madison, and one of the major topics we did work together on is this topic of resolved photons. So this is what I want to talk about. First, I'll give you a brief introduction what resolved photons actually are, then applications to HERA and to plus and minus colliders, and then at the end I'll give you a brief outlook. So what are resolved photons now? You learn about photons in your introductory quantum field theory class or particle physics class. They are introduced as point-like gauge bosons, having this very well-known coupling to the fermi and anti-fermi pair. That's sort of the definition of what a photon is. And that, of course, works both for leptons and for quarks, which is fermions. So now let's consider the case where the fermions indeed are quarks, and expand this diagram a little bit to have one of these quarks interact with another parton, as happens, for example, in photon-proton collisions. Now consider a kinematic configuration where this quark and this gluon have large and opposite transverse momenta. This means that this anti-quark here is collinear with the photon, which means that the incoming quark, this line here, is also collinear with the photon and basically on shell. That gives you a classic collinear divergence, which you have to absorb in QFT, the QFT rules, into some pattern distribution function, which in this case clearly would have to be a quark density inside the photon. And exactly the same way as you do for pattern densities in the proton. If you look at a different configuration where this quark and anti-quark have large and opposite PTs, that would mean that this outgoing gluon is collinear with the incoming gluon, and this exchange gluon is also collinear. That gives you another collinear divergency, different part of phase space, and that collinear divergency, of course, you absorb into the PDF of the gluon. In fact, it contributes to the well-known DGLAB evolution of the gluon densities. So formally, this is really the same thing. If you need gluon density to absorb this collinear divergency, gluon density in the proton, then you need also quark density in the photon to absorb other collinear divergencies. Okay, that's sort of a formal argument. More phenomenological, you can also remind yourself that there are neutral vector mesons, which have spin and charge quantum numbers identical to that with the photon. So you can have transitions between a photon and one of these vector mesons, and vector meson is like a hadron, so you can take a quark out of that. That gives you another motivation to consider a quark density inside a photon, in this case a purely non-perturbative argument. So what are some properties of this Parton distribution function in the photon? They are in fact quite different from the ones in the proton. First of all, it all starts with this gamma q bar vertex. So the PDFs and the photon are all of order alpha electromagnetic, which tells you right away that there is no momentum sum rule, because to order alpha em to the 0, the photon is still just the photon. So most of the momentum of the photon is carried by the bare photon, not by the hadronic part. So the hadronic part by itself does not have to satisfy any momentum sum rules, unlike the PDFs in the proton. Another very important fact is that the PDFs in the photon are of order 1 over alpha s, so alpha s inverse. That's because there is a large logarithm appearing due to this collinear splitting. Phenomenologically speaking, you can say you have to normalize it or regularize it by some sort of hadronic scale, like the QCD scale, that gives you a large log q over lambda, which is something like 1 over alpha s. And that can also be made more formal, and that's done by Witten in 1976, and this is indeed the string Witten. He started his life as a QCD physicist as well. Okay, so we learn then from that altogether the PDFs in the photon are of order alpha electromagnetic order over alpha strong. And early constraints on these PDFs came from deep inelastic scattering experiments, where in this case you have 2 photons, so you have one almost a real photon emitted by an electron that's scattered at very small angle, basically goes straight ahead. So this photon is basically on shell. Then you it can have an hadronic structure, and is probed by a deeply virtual photon emitted by an electron that's scattered at a large angle. So that's just the standard DIS diagram, except that here really you take a quark outside of a photon rather than from a proton. So experiments like that started in around 1980 or so. So our interest was not in this deep inelastic scattering. As I said, this had been done before. We were interested in photoproduction. And our first work on this was on applications of HERA. HERA was an electron-proton collider at DAISY, and it operated in the early and mid-1990s. And we started working on this slightly before HERA started to go into operation. So because of this feature that the Parton densities and the photon are of this order, then it turns out that the direct contribution, which of course still exists, where the photon and the gluon both couple, for example, couple to this hard 2 partons, which then give you 2 high-PT jets, and this resolved contribution, where you take a parton from the photon to make these 2 high-PT jets, they are of exactly the same order in coupling constants. This is obviously one electromagnetic vertex, one QCD vertex, so it's order alpha em alpha s times some parton density in the proton. Here is a pure QCD 2-to-2 scattering, so it's order alpha s squared times parton density in the proton times parton density in the photon. And this one here gives you a factor, as I said, alpha em over alpha s. So altogether, you get the same order of magnitude in both cases. So this is not higher order correction. It should be considered in the same footing. And as we found, I should say also that it has a different topology, because when you take out a parton from the photon, there's always some stuff left behind for color conservation, for example. A photon, of course, is a colorless object. You take a color particle out here, there must be some colored remnant, leave some sort of beam remnant jet, just like you have on the proton side. So when you have this direct diagram where photon couples point-like, you have these 2 high-PT jets plus 1 proton remnant. In the resolved case, you have these 2 high-PT jets plus a proton remnant, plus in addition the photon remnant. Unfortunately, the remnant, of course, go in direction of the beams, basically, and much of them goes down the beam holes where our experimental friends can't build detectors, obviously. So here's an example application for HERA. for different parameterizations of photon structure functions. And in the early 90s, there was a minor industry of parameterizing these things. But the important point here is, so this is the ratio of the resolve to the direct contribution to the dijet production as a function of the jet of the PT for some range of rapidities. And you see that the resolve contribution actually dominates for jet PTs up to about 25 or 30 GeV or so, and can exceed them by a factor of 5 or 10, the direct contribution. Again, this is not a small correction. This is really an order 1 effect that you have to include. And in fact, if you do include this and also do analog corrections to that, the first group that did this was Patrick Orange et al. In France. You could be shown that you could reproduce this photoproduction data from HERA pretty well. Now, in E plus and minus colliders, of course, you have then 2 electrons, or E plus and E minus, each of which can emit a quasi-real photon. So then will then give rise to 3 distinct classes of processes: a direct one, where both photons couple point-like, one where one is point-like and the other one is resolved, or both can be resolved. And here you have no beam remnants, 1 beam remnant, 2 beam remnants, sorry. Now, because typically when an electron emits a quasi-real photon, the photon energy will be significantly smaller than that of the electron. So the center of mass energy in the gamma-gamma system is typically much smaller than that in the plus and minus system. So we did this work in the early 1990s. The plus and minus colliders operating then were this Tristan collider at 60 GeV, LEP1 at 91 GeV. The energy in the gamma-gamma system was then only enough to make quite wimpy jets, or mini jets as they were often called at the time, of a few GeV transverse momentum, not like the 500 GeV jets that you see at LHC now, of course. But nevertheless, this formalism based on perturbative QCD did work pretty well, for example, at Tristan. In fact, in the early 90s, Rohini and I were really quite popular in Japan because this Tristan collider, other than that, was really pretty much a complete loss. I don't think it did very interesting physics. Of course, also because it was overshadowed by LEP just a few years later. And it smartly had put itself into the minimum of the cross-section for annihilation events. Anyway, so here's some example from a publication by the AMI collaboration. This is one of the 3, I think, collaborations, detectors operating at the Tristan collider. And you see here, including these resolved photon contributions, you could describe the data going down to like 3 GeV or so quite nicely. And here you found that resolved photon contributions dominate for up to 5 or 6 GeV or something like that, depending on the pattern distribution functions, optimization. Now, at future plus and minus colliders, of course, the center of mass energy is lots higher than at the, or hopefully will be lots higher than at the previous one. So proper jets will then be formed also in gamma-gamma collisions, presumably. Of more importance is that for a fixed center of mass energy in the 2-photon system, the fluxes will also go much higher than at previous colliders, especially at linear colliders where the so-called Beamstrahlung phenomenon occurs. This is actually a horrible word, really. I don't know who dreamt this up, because Strahlung in Germany is already radiation, so beam is also radiation, but that means, yeah. In any case, this is an emission of real on-shell photons that occur when one of the very tiny bunches gets into the quite large electromagnetic field of the other bunch, and then it's sort of a Bremsstrahlung effect on these bunch-bunch interactions. And that, for some of the designs that were floating around in the early and mid-1990s, that could increase the effective 2-photon luminosity by factors of 10 or 20 or so. And then you got really very large gamma-gamma luminosities, and correspondingly, it could then lead to a very large rate for soft hadronic events from gamma-gamma collisions, even to the extent that for each bunch crossing, you would get one or more of these soft hadronic gamma-gamma collisions. And that's something to be avoided at the plus and minus colliders. One of the nice features of the plus and minus colliders is that when you see the final state, at least for the existing colliders, you can assume that pretty much everything in the final state comes from the hard annihilation. And that's a very nice constraint, of course, on kinematic reconstruction. If you have this sort of event pileup happening here, then you could no longer make this assumption, and that would complicate your kinematic reconstruction quite significantly. So that's something to be avoided, I think. So that's something we pointed out in 1992 in our second joint PRL paper. Now, finally, I guess I'm even a little bit fast, get our coffee earlier, outlook. So in these calculations that I presented so far, we always took the so-called Weizsäcker-Williams approximation, where you assume that you really produce on-shell photons or emit on-shell photons from the electrons or positrons. So you ignore the virtuality of these emitted photons. However, that's not necessarily a very good approximation, because just from kinematics, the virtuality of the emitted photon, p gamma squared, is at least of order m electron mass squared, or that's very small compared to QTD scale, so that you could put sort of 0, that doesn't matter. But the upper bound is something of the order of theta squared times the beam energy squared, where theta is the maximal scattering angle, where you cannot see that you have actually, the electron does not hit the detector. So any theta less than the theta maximum will contribute to the, what's called the no-tag event, and therefore to these quasi-real photons, except that, as I said, they aren't really that quasi-real. And as soon as this virtuality becomes of the order of hadronic scales, the parton content of the photon begins to go down. That one can actually show and calculate. So somewhat better would be actually to not talk about directly photon contents of the photon, but really what you have here is electrons after all. So you can talk about parton content of the electron, which is a convolution between the emission probability of that the electron emits the photon with a given virtuality and the parton content of this slightly virtual photon integrated over the virtuality in this range. It depends then on your experimental circumstances. And of course, you still probe it at some large scale Q, like the PT of the jets that you're producing or whatever. Like, you always need some short distance scale if you want to do perturbative QCD after all. So that concept we worked out and in some detail, and this paper is in fact still being cited now, 30 years later, partly in connection with multi-TV muon colliders. Because muon is also a lepton, it also emits photons. But if you have really are very adventurous and dream about 10 TV colliders, then the muon can also emit a W or a Z boson quite easily. And then you would also have to talk about the parton content of W and Z bosons. And some work along this line is being done, for example, by Tao Han, and his group is one of the great proponents of this multi-TV muon colliders. So they are in this sort of direction, then this work that Rini and I did nearly 30 years ago, more than 30 years ago actually, will still then find some continuation, I guess. Thank you.